For centuries, we viewed electrons strictly as tiny billiard ball particles. But in the 1920s, a revolutionary idea suggested that matter might behave like a wave. Today, we explore the landmark experiment that proved this quantum reality. The experiment used a heated filament to emit electrons, which were accelerated by a high voltage toward a solid nickel crystal. A movable Faraday cup detector was positioned to measure the intensity of electron scattering at different angles. Bragg's law explains that constructive interference occurs when the path difference between waves reflected from successive atomic planes is an integer multiple of the wavelength. This creates peaks in intensity at specific angles. If electrons were just particles, they would scatter randomly in all directions. However, if they are waves, they will reinforce each other at certain angles and cancel each other out at others, creating a distinct pattern. Davisson and Germer observed a sharp peak in the intensity of scattered electrons at an angle of 50 degrees when using an accelerating voltage of 54 volts. This unexpected peak was the smoking gun for wave behavior. Using de Broglie's formula, the theoretical wavelength for a 54-volt electron is approximately 1.67 angstroms. This calculation provides the baseline for comparing our experimental observations with the theoretical wave model. Let's see how voltage affects wavelength. If we increase the accelerating potential to 100 volts, the electron gains more momentum. As the denominator increases, the wavelength drops to roughly 1.23 angstroms. This inverse relationship is crucial. Faster electrons have higher momentum and shorter wavelengths. This principle is what allows electron microscopes to see objects far smaller than what visible light can resolve. We can also work backward. By knowing the electron's wavelength and the crystal's atomic spacing, we can predict exactly where the intensity peak will occur using the Bragg equation. The Davisson Germer experiment proved that electrons aren't just particles, they are quantum objects exhibiting wave-particle duality. They travel as waves but interact with the detector as discrete particles. To summarize, the diffraction of electrons by a nickel crystal provided the first experimental proof of matter waves. This discovery earned Davisson the Nobel Prize and fundamentally changed our understanding of the universe. Quick check: if you double the velocity of an electron, its wavelength is halved. This is because wavelength is inversely proportional to momentum. Did you get it right? From understanding atoms to building modern electronics, the wave nature of matter remains a cornerstone of science. Thank you for exploring the Davisson Germer experiment with us. Generated by Vision Solve AI.